Okay, here's a quick example of resistivity. The space between the two metallic coaxial cylinders of radii A and B is filled with a material of resistivity ρ. What is the resistance between the cylinders? So we're trying to figure out if the charge is flowing between these cylinders, what's the resistivity between them? This is how we go about solving this. Firstly, the equation R equals ρ length over A cannot be used directly because the cross section through which the charge travels varies from 2 pi RAL at the inner cylinder to 2 pi RBL at the outer cylinder. Instead, we consider a thin cylindrical shell of inner radius R and thickness dr. So we're going to consider this small shell here, dr. So we've got R out to here, and the little bit extra is dr. So dr is the thickness of the shell, the length of current path through the shell. So that's the length that the current will pass through, and L is the length of the cylinder here. So the area A is then 2 pi RL, and the length of the current path through the shell is dr. Thus, using equation 1, the resistance dr of the shell is dr ρ times dr over 2 pi RL. Current must pass successively through each one of these infinitesimal coaxial shells. So the total resistance between the two cylinders is the sum of the resistances of all the shells. So we're going to go through all of these shells now from RA here out to RB. So then we just define the integral here from B to A. We pull out all the constants, and the only thing we're left with is 1 over R. Well, the integral of 1 over R is ln, and then we put in the constants of integration. We end up with ln B over A. So then that here, given B and A, the values B and A, whatever they might be, we can solve for the resistance R. So the shell resistances simply add up. So all of these resistances from each shell add up, and we find the total resistance. So there's an example using the equation of resistivity in terms of ρ, length and A.